Hello everyone, and welcome back to another episode of the Math Lead Academy. Today we'll be going over Chapter 16 in your textbooks, which is about measurement. In this chapter we will cover how to calculate area of 2D shapes, find surface area and volume of 3D shapes, and how to convert between different units of measurement, such as centimeters to millimeters, hectares to square meters, and so on and so forth, in order to help you in your measurements both in real life and in this course. We'll also be having a quick look into how to write in scientific form, such as 10 to the minus 6 meters, and what this actually means. Let's go over some revision of some shapes that you might know and how to calculate their area. So a parallelogram, the formula to calculate the area of this parallelogram is just base times height. And when the height that we're using here is not the height of the slanted side, so it's not this, it's the perpendicular height, so how tall it is like this. In order to calculate this, we can use Pythagoras' theorem. If we have the length of this little segment here, and we have the length of the slant, we'd be able to find this using Pythag, because this is obviously a right angled triangle. So here it would just be the height squared would just be equal to the hypotenuse, which is the slanted side. So I'll just call the slanted side S, minus, we'll call this little bit A, minus A squared. But obviously that's just more for that. But you're unlikely to get given the slanted height, but that's just for some distinct scenarios. Anyway, just make sure that you're always using the perpendicular height and not the height of the slant, or the length of the slant. Obviously, you just write it, this is how you write it algebraically. And then next for a triangle, once again it's the perpendicular height. And this time it's half times base times height. The reason it's half here is because obviously if, let's just say you have a triangle like this, it's a right angle triangle. If we were to fill this in, this would be a square, right? And now you can see how a square, obviously, remember, it's length times width, or in this case, we can call this the base, and we can call this the height. So a rectangle here would be base times height. And so a triangle, which cuts it in the middle, would be half of this, which is why our formula is half base times height. And this also works, just say if we have, let's just draw it on this triangle, let's draw it like this. We've just created another one of these shapes, so now I have two of them. This is base times height, because this is now a parallelogram, which you discussed as having the formula base times height. And since this triangle is half of this means the formula for we can deduce the formula of a triangle is half base times height. Trapezium, we take basically what we want to do for a trapezium is it's the perpendicular height once again. But this time we're taking the average of the two sides right here. So base 1 plus base 2 divided by 2, or times by 1/2. And we're basically just taking the average length of the bases and heights to get this formula. So it's just half, in brackets, base 1 plus base 2 times the perpendicular height. Now, for a rhombus, the formula for area of a rhombus is just half times d1 times d2. Obviously, once again, we can use a rectangle in order to show how this proof works. So if we just draw a bigger rectangle outside like this, and so d1 right here is the length of this diagonal right here, and d2 is also the length of this diagonal. Sorry, it's meant to be the whole thing. So that's d1, this is d1, and this is d2. So obviously, as you can see here, the length d1, d1 is the width here, and d2 is the height. Now, obviously, remember that it's length times width for the formula of a rectangle. So here it would just be d1 times d2. But obviously, see how we have triangles in each of these quadrants? that means we're only using half of the area for each one. So this is why our formula is half d1 times d2, with d1 and d2 being the internal diagonals. Similar story for a kite. I could draw another set, but it's just half d1 times d2, and I could draw another rectangle in order to prove this. Now, for a circle, the formula for area is pi, which is our mathematical constant, which is approximately equal to 3.141, times radius squared. And the radius is just the length from the center of the circle to the edge, or the circumference. You should know all of these formulas, but this is just a little bit of a revision, and we can practice using some of these shapes here. So we're going to try and calculate the surface area of some of these shapes. So this one, first one up, is a trapezium. So remember, it's half b1 plus b2 times height. We have our perpendicular height here of 3 centimeters, and our two bases are 2 and 5. So it's half, 2 plus 5 is 7, half 7 times 3. So half of 7 times 3 is just half of 21, which is approximately equal to 10.5 centimeters squared. And make sure you're doing it in centimeters squared. Make sure you always include your units, because we are doing a measurement calculation. Here, just something I forgot to mention about when you're finding the length of circles. So when you're trying to find the area of a circle that isn't a full circle, you just do the amount of degrees over 360. Because in this case, when we have 120 over 360, because 360 is a full circle, right? Or the full amount of degrees in a circle, this means we simplify this down, we have 1/3. And basically what we're saying is that we have 1/3 of a circle, because if you multiplied this area by 3 and you turned it around, as you can see like this, you'd have a full circle where it would be, our formula of pi r squared. So, when you're trying to calculate the area of a particular sector, it's just x, your amount in degrees, over 360 multiplied by r squared pi. Now, obviously, going back to what we had, it simplifies down to 1/3. So we just do 1/3 times r squared, which in this case is 10. So 10 squared pi, which is equal to 1/3 times 100 pi. So it's just 100 over 3 times pi. Now, obviously, you can simplify this down using a calculator, and I'm going to be doing so. So it's just 100 divided by 3 multiplied by pi. Just using the simplification of pi, and in the end, we end up getting it's approximately equal to 104 centimeters squared. Now, finally, we're going to try and find the area of this kite. Remember that the formula for area of a kite is just half times the two internal diagonals d1 and d2. So what we're going to do here is we're just going to do half multiplied by 15 times 30. That gives us just 15 times 15, which is 225 millimeters squared. Remember, it's in millimeters here, not centimeters. Just make sure you're always checking your units and writing it in units squared. Just making sure you're all working the same unit to make it nice and easy. Now, when you're trying to find the surface area of certain 3D objects, like a prism, what you want to do is you want to sum up the areas on all of these individual faces. And usually in prisms, they'll have 6 faces. But what can you notice about some of these prisms? They have, in these regular prisms, they have the same sort of shape on these two sides. So these two sides have the same shape. This side right here has the same shape as this side, meaning they'll have the same area. And finally, this side also has the same area as this side. So what we can do is we can actually just do 2 multiplied by each of these sides, so the area of each of these sides, so area 1 plus, I'll do a different color for the different side, area 2 plus area 3, and multiply it all by 2 to get a very simplified formula in order to calculate these surface areas. So as you can see here, this is just another form of expressing what I just said. This is in particular a regular rectangular prism, where you can what you do here is you have your lengths A, B, and C for your and then what we do here is that we have AB, which is just this area, because this is one rectangle. Obviously we have it once again repeated on the back. Then we also have BC, which we can say is this area, and it's also repeated on the back over here. And then we have CA, and the area is repeated on the bottom here. And then obviously you just do 2 multiplied by each of the areas, so AB plus BC plus CA, and that is the same formula that I was kind of hinting at earlier. But obviously there's going to be exceptions to these rules, such as this triangular prism right here. And what we'll do here is we just add up these 2 faces, because obviously they repeat, and then see how you have 3 individual faces here. And then what you have to do here is you just need to use side lengths here multiplied by the height, which should be the same amongst all 3. Obviously, in this triangle, I'll have different side lengths, and then you just add all of these areas up. There's no particular formula. For surface area, you just need to know what you're doing. So for the example, this triangular prism, we've got 1 set of repeating shapes. We've got 1 here, so 1, 2. This repeats, and then we have to calculate individually the surface area of the other 3 shapes, which are all rectangles in this case. So here it's just 2 times the area of these 2 triangles, so it would be half 6 times 8 base times height, remember this. And then obviously these 2 will just cancel, because it's 2 multiplied by half, so these will just cancel out. 6 times 8 plus, and now we have our 3 length times width, because they're all rectangles. So we have 20 times 8 plus 20 times 6 plus, and finally this slant right here. This area right here, obviously you have a right angle triangle. We're going to have to use Pythagoras, because this is the long hypotenuse side. So you have c squared equals 8 squared plus 6 squared, which is just equal to 100, and then c is the square root of 100, which is 10, so it's just 10 times 20. Right, so this simplifies down to 48 plus 160 plus 120 plus 200, which equals, if I can just crunch the numbers, it's pull out my calculator. So 100 plus 160. It's just equal to 528 square centimeters. Now we can try again for this shape right here. Here we have, again, 1 trapezium that repeats across 2 faces. Then we have to calculate the area of the other 4 faces which are all distinct from each other. So let's just try and calculate the area of this trapezoid first. So remember, half plus the two bases. So we've got... Now interestingly here, it doesn't appear to give the top length. So what we can do, we can try and manually calculate what this length should be. So we've got 13 centimeters here, and we're trying to calculate the height. And we've got 12 centimeters here, just forming up this triangle. We're just trying to find what this length is on the bottom to take it away from the top, because it's 16 centimeters minus this area will be the length of this on top. So it's just 13 is our hypotenuse, and then 12 on the side. So it's just 169, which is 13 squared, equals 144 plus 8 squared, which is our missing side, A. So here, A squared equals 169 minus 144, which just gives it 25. So in this scenario, A equals 5 centimeters. Therefore, we take A off of the bottom length to get the top length here as 11 centimeters. Now that we have this, we can start to crunch these numbers. So our two bases are 11 plus 16 times our perpendicular height of 12. That's there. And then we multiply this all by 2 because there's 2 of them. Obviously, we can cancel out the half and 2. Plus, now let's just try and find the length of the other side. So we got 16 times 4 on the bottom, plus 11 times 4 on the top. Then we have 13 times 4, because this is our length here of this slant. So we've got 13 times 4. And finally, we have 12 times 4 as our last length. So obviously you can crunch this all down, and this will give you your surface area of this shape. So let's just use a calculator. I want to make this nice and easy for us. So what we'll do is we've got 11 plus 60 times 11 plus 16, which gives 27. 27 by 12 plus 16 times 4 plus 11 times 4 plus 13 times 4 plus 12 times 4. In conclusion, you get 532 centimeters squared. And you can correct me if I've gotten this wrong. Alright, now in order to find the surface area of a cylinder, what you need to do is, you see how you have these two faces right here? Obviously these are just our circle lengths, circle area, sorry. Remember, it's pi r squared, and since these repeat, it's 2 pi r squared, plus we need to find the area of this curved face that wrapped around. When we unwrap it, it's just equal. As you can see here, it just becomes a rectangle, which is equal to the circumference, because this is obviously the length of the circle that it curves around, multiplied by the height. Because when you unroll it, this just becomes the circumference, right? So obviously your circumference of a circle is 2 pi r, so it just becomes 2 pi r times h. So it's actually just 2 pi r squared plus 2 pi r h, and this is the surface area of any cylinder. So we can use this formula in order to calculate some of these here. So obviously we have our two areas here, which fall under 2 pi r squared plus, obviously we find our circumference, 2 pi r times h. This is our formula. So from here, 2 pi r here. So our r, obviously 10 centimeters is our full length. So our r is only going to be half of that because this is our diameter. So our r value is 5 because obviously 2 times your radius gives you a diameter, and half of your diameter is your radius. So half of this is just 5. That's our, so 2 pi times 5 squared plus 2 pi times 5 times 25, and this should give us our surface area. So it's just, this simplifies down to 50 pi, and this simplifies down to 5 times 25 is 125 times 2 is 250 pi. So in conclusion, this just becomes 300 pi centimeters squared. Now obviously we can simplify it using pi, but if you want to leave it in terms of pi, such for an example, if you don't have a calculator, you can leave it in terms of pi centimeters squared. And so this will be your answer, but if you want to use a calculator, I'll just quickly just see what this is. So 300 multiplied by pi gives us approximately 942 centimeters squared. I'm rounding to 3 significant figures here. Now, what we're trying to do in order to find half a semi-cylinder right here. Obviously, we only have half of said surface area that we usually find, and we also have half, because remember, it's just you've only got half a circumference here, so it's half of this, and then you also have to add in the surface area of this rectangle on top. So let's try and find these first. So our two semicircle areas are 2 squared. However, obviously it's only half of each, so actually the 2 and the half will just cancel out. So we just have pi r squared as our area of these two semicircles combined. Then we have half our circumference, which is just pi r. This is usually 2 pi r. Pi r times the height, which is 15 centimeters. Plus 6 times 5, so it's just length times width. Now, let's simplify this down. We got pi r squared. R is just 3 in this circumstance, because obviously, remember, it's half your diameter. So 3 squared is 9, so this just simplifies down to 9 pi plus, we got 15 times 3 here. So that just gives us 15 times 3 is just 45. So we've got 45 pi plus length times width is just 6 multiplied by 15, which approximately is 90. So we squared. Now let's just simplify this all down. We have 9 plus 1 is just 54 pi plus 90. And this gives our surface area, which 54 pi times 54 plus 90 is 200, is approximately equal to 260 centimeters squared. This is just rounding to 3 significant figures once again. Now, when we're trying to find the volume of a 3D shape, what we want to do is we want to find the cross-sectional area, so the area that repeats across, and then we just find the height. So it's just volume equals the cross-sectional area A times height, or the area of the base. whatever you want to call it. This holds true for any sort of prism. So in specifically rectangles, obviously your area formula is length times width. So our volume formula is just length times width times height. For a triangular prism, it's just obviously our area is half base times height. So obviously here we'll just assign that height, and then we'll assign this to being depth. I'll just say D, BHD, and your height is just your perpendicular height here, H. I hope this makes sense. And so this is your volume of your triangular prism. Now, obviously, when you come down to the volume of the cylinder, it's just your circular area repeated across this height. So obviously your circular area is pi r squared. So it's just pi r squared times height. And that is the formula for area for volume of a cylinder. Now let's try and calculate some of these. So obviously remember, it's just area times height. Your area is given 12 centimeters squared times 20. So your area for this, so the volume of this shape is just 12 multiplied by 20, which if we put this into a calculator, obviously you can do this by hand, but I'm just being a bit lazy, is 240 centimeters cubed. Centimeters cubed now, because we're dealing with volume. Here, it's all you need to do is calculate the area. So the area here is interesting because you've taken a little circle out of this bigger circle. So what we do is we calculate area of the bigger circle. We'll put radius big minus the area of the small circle. Radius small. So radius of the big circle, just covering this, would be 2 meters. For the small circle, it's only 1, because obviously you just take half the diameters shown here. So it's just 4 pi minus pi, because 1 squared is just still 1, 2 squared is 4, so it just becomes 3 pi. Then obviously we've got our area of 3 pi centimeters squared. Oh, sorry, not centimeters, it's meters here. Just make sure you're paying attention to these units, or you can stuff it up like I am. So it's 3 pi meters squared times 10 meters, which gives us 30 pi meters cubed. And obviously you can simplify this down using a calculator if you want to. Now, conversions between units, these are important. Obviously, when you're converting from kilometers down to meters down to centimeters, it goes down by a factor of 10 each time. So we've got 1,000 times 100 times 10. Then from meters to centimeters, it's 10 divided by 100 divided by 1,000. Obviously, this pattern doesn't follow for all things, but just for your millimeters, centimeters, meters, and kilometers, it's helpful to remember. Now, when you're going in centimeters squared, you got to divide by the value squared. You got to square the value, right? Because if, for example, let's just say we have obviously 10 millimeters in centimeters, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This isn't the best representation, but these are your millimeter values right here. This is 1 centimeter. So if we have 1 square centimeter, it would just be this repeated, right? So you got 1, 2, 3, 4, 5, 7, 8, 9, 10. But can you see the issue here? Obviously, 1, 2, 3, 4, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But can you see how 1 square centimeter, so 2 square centimeters, is actually 10 millimeters multiplied by 10? Because we're obviously this is a square value, so it's just 10 squared. This is what we're dividing by, because there's 100 millimeters squared in 1 centimeter squared. Does this make sense? I hope it makes sense. But if you just like imagine this to be a square factor, this is why we're doing it by factors of 10 squared, or factors, and then for volume it just becomes that but cubed for a very similar reason. Obviously you have 3 dimensions and you just have 1,000 millimeters cubed per centimeter cubed. Now hectares are a special unit for area. It's just 100 meters by 100 meters. And then since it's 100 meters by 100 meters, it's not so it's 100 meters by 100 meters. This means it's 10,000 meters squared. Obviously, this is not 10 kilometers squared. Do not make this mistake, because remember, when we're converting meters to kilometers, we have to divide by 1,000 squared. So it's actually would be a million. A million square meters is 1 square kilometer. You just need to remember that. So it's just squared. So instead, 10,000 square meters is 1 hectare. This does equal 1 hectare. And so, obviously, if you multiply this by 100, you would get your million square meters, which is 1 kilometer. So therefore, 100 hectares is equal to 1 kilometer squared. And obviously you can see up here, it's equal to 1 kilometer squared. Then also we have our special thing, which for volume, which is liters. Obviously, this is just 1,000 cubic centimeters, because this does not equal 10 meters cubed. Because remember, this does not equal 100 meters, 10 meters cubed, because usually, when you might think that, because centimeters to meters is dividing by 100, but remember, it's 100 cubed. So 100 cubed is actually a million. So there's actually 1 million cubic centimeters in 1 square meter, 1 cubic meter of liquid. So one liter, remember, is just 1,000 cubic centimeters, and 1 milliliter, which is the thousandth of a liter, is equal to 1 cubic centimeter. And also, remember that 1,000, and since when you multiply 1,000 cubic centimeters by 1,000, you get to a million, which is equal to 1 cubic meter. 1,000 liters, which is 1,000 times this value, because remember, 1 liter equals to 1,000 cubic centimeters. 1,000 liters is equal to 1 cubic meter of a fluid. So with this, we can do a few quick conversions. So let's just say we have this area. It's just it's just length times width. We'll just calculate this using a quick calculator. 111,800 meters squared. So this is your square meter calculation. Now to convert this into hectares and square kilometers. So hectares, remember, it's every 10,000 meters. So you just divide this value by 10,000. So it just becomes 11.18 hectares. And then for square kilometers, you're dividing by 1,000 squared, or a million in this case. So you're just dividing this value by a million, so 0.1118 kilometers squared. Now over here, with your liquid calculations for volume, we'll just practice some conversions. So remember, meters to cubic meters is just multiplying by 100 cubed or a million. So this is actually this value here becomes of 560,000 cubic centimeters. Then for cubic meters to liters, obviously remember this is multiplying by 1,000, so it just becomes 620 liters. Then cubic millimeters to ml. So remember that your milliliters, equal cubic centimeters. So we just need to convert to cubic centimeters, which is just multiplying by 10 to the 3. Oh, in this case, sorry, it's dividing by 10 to the 3, which is just 1,000. So in terms of milliliters, we have 52 milliliters from 52,000 millimeters cubed. And finally, converting liters to meters cubed is just dividing by 1,000. So we just have 0.96 meters cubed. Over here, we just want to have a quick look in terms of scientific notation and your prefixes for some of these units. So we've got kilo, mega, giga, tera, penta, and these are just your symbols of power in order to express them in terms of like units. So if we have something like a kilometer, it's just 10. It's just 10 to the 3 of the SI unit, or the standard unit, which in this case is a meter. So it's just 10 to the 3 meters, right? So 1 km equals 10 to the 3 meters. And this continues down, so a mega would be, so 1 megameter, which is just a capital M, would be equal to 10 to the 6 meters. And this is how you express it in like the basic unit of meters. So obviously you have milli, micro, nano, pico, femto. And then obviously it's just 10 to the minus 3 meters. Or so you've got this is the same thing as 10 to the minus 3. It's just 1 times 10 over 3 meters. So it's just like a fraction of said meter. And then you can obviously convert into each of these. And then when expressing your values in scientific form, obviously you want to use meters or meters squared or meters cubed, because meters is the basic value. And then you just use your powers right here in order to express it scientifically. So we'll just convert, and then we'll always want to make sure you're converting down to the nearest value, just one number in front of the decimal point. So for example, 6.7 times 10 to the 3 meters. This is how you write it in scientific form, making sure that you only have one value. So this value right here, we'll call it the x value. You want to have your x value, it needs to be in between 1 and 10, but it can't be 10, right? Because then 10 would just become 0.1, and you'd add it on to the prefix up here. So you can't have something like 101 times 10 to the 3 meters. You would just, basically what you would do is you would put like a decimal point right here. Then you'd have you'd obviously be dividing this by 10 to the 2, so you just multiply this back into here, so it becomes 10 to the 5. So it would just be 1.1 times 10 to the 5, because 10 to the 3 times 10 to the 2 is just 10 to the 5. I hope this makes sense. So, for example, we have 23 millimeters right here. So it's just, so milli, obviously it's 10 to the minus 3. So 23 millimeters would be 23 times 10 to the minus 3 meters. And then obviously what you do here is you just put the decimal point right here, so it would just become 2.3 times 10 to the minus 2, because you're dividing by 10 to the 1 here, so you've got to multiply 10 to the 1 back into here, and 10 to the 3 times 10 to the 1, just 10 to the minus 2, obviously. And that's how you get your value, your scientific value right here. Let's try one more. We've got 651 nanometers. Obviously, your nano is 10 to the minus 9. So it's 651 times 10 to the minus 9 meters. And we'll just convert this down. So divide this by 10 to the 2. Put this back in here, so it becomes 10 to the minus 7. You get 6.51 times 10 to the minus 7. I hope this all made sense, and this has just been another episode of the Mathlete Academy. Thank you for having me.